Greetings, welcome to Machine vs Mathematics channel. Fourier series made our life very simple, right? See, for example, you have a non-sinusoidal periodic function, say in the time domain. And if you're giving this quantity as input to linear time invariant system, the steady state response of that system we can find out very easily using Fourier series techniques. Yeah, because any non-sinusoidal periodic function we can express in the form of infinite number of sines and cosines if at all there exists DC as well. Okay, and this made our life very easy because see, if input is sine, output is always, that means if input is sinusoidal quantity, output is also sinusoidal quantity. That means output is always guaranteed when there is input a sine quantity. So with this beauty and with the help of time shifting property, we can try to solve out a very decent question asked in GATE Electrical 2008 for 2 marks. Yeah, let x of t be a periodic signal with time period t. Okay, and y of t is given like this, linear combination of shifted version of our x of t. Okay, now the Fourier series coefficients of y of t are denoted by b sub k, and whatever, if b sub k is equal to 0 for all odd k, then t naught can be equal to, you have 4 options for 2 marks. It is very simple to solve. There is no big deal in solving this simple problem. Yeah, Fourier series problems looks like weird kind of thing, but if you know how to apply properties and all, you can solve it in no time. Okay, so anyways, let us accept the given y of t like this. So before we accept y of t, we have to first of all accept this. X of t be a periodic signal with time period capital T. Let us say like this. Let us take x of t as this. Now its continuous time Fourier series. Its continuous time Fourier series be a sub k. Okay, of course you have this x of t. This fellow is periodic with some period capital T. Okay, and you also give like this. You have y of t whose Fourier series coefficients are given like this. So y of t whose Fourier series coefficients, plural form, right? I may have more than 1, 5 or 100, whatever. Generally we have to take this way, ak, Fourier series coefficients, and also Fourier series coefficients like this. Okay, so b sub k. This is what given to you, and also he gave us y of t expressed as linear combination of shifted forms of input, x of t minus t naught, x of t plus t naught. We know very well shifting in one domain is nothing but multiplication by exponential in the other domain. Okay, so as y of t, see, as x of t is periodic, now you have linear combination of these two, so we also assume y of t is periodic. See, as y of t is periodic, therefore he is mentioning that y of t is denoted by Fourier coefficients pk, because Fourier series can be strictly, we can apply Fourier series techniques only over periodic functions. Okay, so anyways, we have this one. Now this fellow, as x of t is periodic with fundamental time period capital T, this fellow is also periodic by same fundamental time period capital T. Okay, now you know what, this need not be always. We have lecture samples. We'll come to know if these two are periodic. If these two are periodic with some fundamental time period capital T, y of t need not be always periodic with same fundamental time period. Anyways, but in this problem we have this stuff like this. So now therefore, if I try to take its Fourier series coefficients CTFS, so what you have, y of t we have b sub k and x of t minus t naught. If x of t is ak, now ak, see, shifting in one domain is multiplication by a power say minus jk omega naught t naught multiplied by Fourier coefficient. This is ak. All right, and similarly here, what do you have? E power positive. I'm just applying properties. There is no big deal here. I have positive t naught, so therefore positive t naught here multiplied by again ak. Yeah, because this ak is Fourier series coefficients of signal x of t. Okay, so therefore now bk is what? So b sub k, this fellow, I can take this a sub k as common, and you have e power positive, this one say e power positive jk omega naught t naught, plus I have e power minus jk omega naught t naught. Now what can I do? I can multiply and divide by 2. If I do this, then we get this fellow becomes 2ak, and this bracket quantity, this bracket quantity is what? Cosine k omega naught t naught. All right, so this is what you have. So finally we have constructed Fourier coefficients for y of t, and those Fourier coefficients are so finally we have done this. So b sub k, so b sub k is equal to what now? 2a sub k cosine, I'm just revisiting that equation again. B sub k is equal to this. Alright, and what is given to you? See what is given to you here. If b sub k is equal to 0 for all odd k, then he is asking us to find this shifting quantity, this t naught. Okay, if b sub k is equal to 0 for all odd k. Now you tell me, when cos becomes 0? When cos is multiples of, say, odd multiples of pi by 2. Yes or not? When cos is odd multiples of pi by 2, so this fellow, this cos becomes 0, hence bk becomes 0. So he gave like this here. So he gave this way, bk must be 0 for all odd k. This is what he gave us in the condition. That is, you see, let me take this fellow out. Okay, so let me make this way. That means, what is omega naught here? Fundamental frequency. Okay, so k omega naught t naught is equal to, I will take this way. Let me take this one as some k times pi by 2. See, again I am taking k because he is saying for all odd k. I want to accommodate something for k here. So therefore, now what happens here? Now anyways, I can make it like this, where k is equal to plus or minus 1, plus or minus 3, alright, plus or minus 5, so on. So otherwise this becomes omega naught t naught is equal to pi by 2. Okay, so we know very well fundamental frequency is 2 pi over fundamental time period. This fact we are well familiar with. You plug in the same here because options we have in terms of fundamental time period in the numerator. Okay, so therefore we will try to use this. Now you have 2 pi over capital T multiplied by shifting quantity t naught is equal to pi by 2. So these two are ruled out. Now what is t naught here? Yeah, so t naught is t by 4, capital T by 4. That's it. So option B is correct. So what did we do? Simply we accepted x of t, Fourier series coefficients as ak, y of t as bk given. So y of t is linear combination of shifted forms of input, I mean x of t. So we have this. Simply we used property of Fourier series. So therefore shifting here becomes multiplication of exponential here and times ak. So this is what we have done, and we have constructed Fourier coefficients for y of t, and we obtained like this. Now he gave this one, bk must be 0 for all odd k. So we know that cosine becomes 0 for odd multiples of this bracket quantity. So I took this one as this k pi by 2. Now k is odd multiples. Okay, this k becomes odd quantity here. So therefore we have this, and hence the delay quantity, or this t naught quantity is capital T by 4. Very simple. Fourier series is very simple to solve and very interesting. Okay, so we will discuss this in our subsequent. Anyways, I'm making a lecture series on signals and systems and also electromagnetic theory, antennas and wave propagations, and electronic devices and circuits, analog circuits, and all these things. So gradually things will come out, and you can check things in our channel, and it will be very useful for competitive examinations and also for higher studies as well. Okay, so thank you very much and bye.